All right, so we're going to end with a couple of concepts here. So let's continue with what we were doing. We started looking at how to evaluate if an ion was acidic or basic based upon its conjugate behavior. Now we can start looking at salts in total. And so simply speaking, there are four different combinations that can exist. So first combination would be that the cation and the anion both are unreactive toward water. So I've got the conjugate of a strong base as my ion, as my metal, and I've got this conjugate of a strong acid as my nonmetal. Neither of them react toward water, so they're both neutral. And the salt, as a result, is going to have a neutral pH as well. The second scenario, which is also common, is that we have an inert cation. So the metal ion is inert toward water. So we're dealing with a conjugate of a strong base. So we've got sodium or potassium, lithium, something like that. But the anion is not. The anion is a conjugate of a weak acid, like acetate or oxalate or sulfide or something like that. Well, in that case, we would have a basic pH for the salt. Because at the heart of this, what we have to remember is that every ionic compound has two parts, the cation and the anion, the positive or metallic component and the non-metallic negative component. Well, the cation speaks to acidity and the anion speaks to basicity. And so if the cation is inert, we have no acidity, then the basic character of the anion would show through. If we flip the scenario, anion is inert, but cation is not. So we have something like iron paired up with something like chloride. Then we would have an acidic solution as a result. So those are the three simplest examples. They're both inert, so it's neutral. One is inert, but the other isn't, so we force ourselves in the direction that is not inert. But what if they're both react? The cation is acidic and the anion is basic. How do I determine the pH and the acidity? Well, I can't just assume that it would default to neutrality, because as we know, acid and base strength has to come into play here as well. What I have to do instead is I have to compare the acid and the base. So if I compare the Ka for the acidic part versus the Kb for the basic part, the larger value will dictate the pH. So if Ka is bigger, then it ends up being acidic. Kb is bigger, then it ends up being basic. If Ka and Kb are similar, then it's going to be near neutral. So your book has tried to put these things down into terms, trying to kind of draw out every possible scenario. I haven't decided fully if I like this table yet, or if I just like kind of the four scenarios kind of possibility. But this is in your book in chapter 14, section 11. If you wanted something a little bit more precise for every single scenario. But let's do some practice here. The easiest way to go about doing this is to split up each salt into its components and figure out where the components come from. So, for example, I can look at this, I can split aluminum nitrate into the aluminum ion and the nitrate ion. And the way that I'm going to do it is I'm going to look at this and say, okay, aluminum came from aluminum hydroxide. What do I know about aluminum hydroxide? Is aluminum hydroxide strong or weak? Well, aluminum hydroxide is not on our list of strong hydroxides. So I've got myself a weak base here. Nitric acid on the other, or excuse me, nitrate ion, its conjugate would be nitric acid. Nitric acid is one of my strong acids. Which side has more strength, acid or base? Acid. So I would expect aluminum nitrate to be acidic. And so that's how I would break down each one of these ionic compounds. What is it made from? Sodium ion, carbonate ion. Conjugate base of sodium hydroxide is, or sodium is sodium hydroxide. I know that that is a strong base. Conjugate acid of bicarbonate or of carbonate is hydrogen carbonate ion. Hydrogen carbonate ion is a weak acid. So the base side wins out here. This is a basic salt. For calcium chloride, I've got the calcium ion and the chloride ion. Calcium would be derived from calcium hydroxide. Calcium hydroxide is one of my strong bases. HCl's conjugate, or chloride's conjugate, is hydrochloric acid. That's a strong acid. If I find myself in this situation, strong against strong, strong equals neutrality toward water, they have equal strength, we would consider this salt to be neutral in pH. All right, for the last one, I've got zinc ion and iodate ion. Zinc ion would come from zinc hydroxide, which is a weak base. Iodate ion would come from hydroiodic acid, or excuse me, iodic acid, HiO3, which is also weak. Now, if I have a weak on weak scenario here, I cannot just call it neutral. We could do that with the strongs because the strongs were so high up in Ka and Kb that their conjugates have no impact on water. So we just say that they're neutral. But in this case, weakness is a variable kind of tendency. How weak are we talking about on each side? And to answer that question, we need to go to a table of values here. So the Kb for zinc hydroxide is 7.94 times 10 to the negative 7th. If I go to if I go to iodic acid, I see that the Ka value for iodic acid is 1.7 times 10 to the negative 1st. The acid character is far better than the base character. We would expect this to be acidic. Okay, so qualitatively speaking, all I need to do is to look at the conjugates of each of the things that are being involved and compare their relative strengths to each other. The stronger one dictates the pH. That's all I have to do if I'm just being asked, tell me if this is going to be acidic or basic. All I have to do is qualitatively evaluate, okay, this comes from a strong base, this comes from a weak acid, the base character wins, it's going to be basic. It gets a little bit more complicated when we actually have to start calculating values. Because when we calculate values, then we have to actually get into the character of, well, what does the conjugate do? I will admit to you readily, this is an oversimplification, but we use it because it works. In reality, what we should be doing is we should be looking at the Kb for nitrate versus the Ka for aluminum. But that's way more complicated just because we would have to do a whole lot more digging into appendix tables to solve questions that really are relatively simple. If we simplify it, we get the right answer, even if we are getting it in a kind of around the corner kind of way. The reality is aluminum nitrate is acidic because the aluminum ion is acidic. Sodium carbonate is basic because the carbonate ion is more basic than the sodium ion is acidic. We have to take that into consideration when we start doing calculations. And so what we want to think about with these calculations of pHs based on acidic and basic salts is we want to evaluate, okay, what is the species that is actually reacting? How is it reacting with water? What does its equilibrium constant look like? And how do we go about using ice tables and what we already know to kind of frame it in? Now, the good news for us is that the calculations themselves are ice table based and very, very similar to the kinds of calculations that we were doing yesterday. In those calculations, where we were just saying, okay, here's the base reacting with water to make the conjugate acid and hydroxide. I can find out the hydroxide concentration, use it to calculate POH, use that to calculate pH. We're doing a lot of the same kind of stuff. The wrinkle to it is that there is one extra step that we have to throw in here to get us to that equilibrium reaction in the first place. The other wrinkle to this is that in very few cases are there Ka and Kb values published for the conjugates. What we'll usually see is a Ka or a Kb value for the acid itself, or a Kb value for the base itself. Well, if its conjugate is acting in the opposite direction, we're going to have to calculate its opposite K. And we do so using that Kw expression that we brought up earlier, where rearranging this, I can find the value of the conjugate by dividing the original into Kw. So let's take a look at some examples here. I have a bottle of chlorine bleach that holds an aqueous solution of a concentration of 82.5 grams per liter of sodium hypochlorite. What is the pH of this solution at 25 degrees Celsius? Well, first thing that we have to do is that this is not a concentration unit that we can use. We're going to have to convert this concentration into molarity. So 82.5 grams over liters. We need to turn the grams into moles to turn it into a molarity. Molar mass of sodium is 22.99. Molar mass of chlorine is 35.45. Molar mass of oxygen is 16. $74.44. Now doing the conversion, 82.5 divided by 74.44. The three significant figures is 1.11 molar. So we have sodium hypochlorite, and it's going to break down into sodium ions and hypochlorite ions in water. Since we're starting with 1.11 molar concentration of that, following the stoichiometry, it would be 1.11 molar sodium and 1.11 molar hypochlorite in that solution. So the question really becomes, okay, of these two options, are either of them pH changing? So if I look at sodium hypochlorite, I have the sodium ion, which is derived from sodium hydroxide. That's a strong base. So strong bases, conjugates of strong bases would have no impact on pH. Okay, so we know that the sodium ion is inert. Okay, what about the hypochlorite ion? It would be derived from hypochlorous acid. Hypochlorous acid is a weak acid, so we would expect that this be basic. So we have our answer. The part of the solution that is pH active is the hypochlorite ion. How does it react? Hypochlorite ion reacting with water would act as a base. So water is going to give a hydrogen to it, and hydroxide is going to be the product of that. The K value for this is going to be determined by, well, wait a second. We don't have a Kb value for hypochlorite. We're going to need to look at the Ka value for the hypochlorous acid. So hypochlorous acid's Ka is 2.88 times 10 to the negative 8th. So 2.88 times 10 to the negative 8th. So 1 times 10 to the negative 14th divided by 2.88 times 10 to the negative 8th. To 3 significant figures, 3.47 times 10 to the negative 7th. Okay, this is all of the new. This is all of the extra stuff that was talked about in the previous slide. From here, we proceed like a normal lyse table, like what we were doing yesterday when we were exploring weak acid, weak base equilibria. So initially speaking, our hypochlorite ion concentration was 1.11 molar. We had no conjugate acid. We had no hydroxide. We're going to lose some amount of hypochlorite, gain some amount of HOCl, gain some amount of hydroxide. So at equilibrium, those would be our concentrations. Now, as has been the case for a lot of our weak acid and weak base equilibrium, 5% rule is in effect here. We've got a Kb value that is on 10 to the negative 7th, and we've got a really high concentration at greater than 1. So you can do the math yourself if you want, but we're on pretty safe footing to ignore that minus X term. So setting up the equilibrium, 3.47 times 10 to the negative 7th is equal to X times X over 1.11. Multiplying each side by the 1.11, I get 3.85 times 10 to the negative 7th is equal to X squared. We're going to square root both sides. And the 3 significant figures, 6.21 times 10 to the negative fourth molar is our value for X. So inserting X into our ice table, we can solve it. Concentration of hypochlorite ion remains at 1.11. Each of the X's are 6.21 times 10 to the negative fourth molar. Questions asking us about the pH though. Since we're talking about hydroxide, we have to find the pOH first. So the negative log of 6.21 times 10 to the negative fourth. Our pOH is equal to 3.207. Again, 3 decimal places because we had 3 sig figs in the concentration. Our pH is going to be 14 minus that. So our pH is going to be 10.793. So again, this is a salt solution. It's a highly concentrated salt solution, but it's still a salt solution. And it's getting us a pH in the almost 11 range. This is why we can't discount the idea of salts being unimportant toward pH. Because of their conjugate behavior, because of their ability to react to water when they are the conjugate acids or the conjugate bases of other weak acids or bases, they are going to be reactive toward water. And in some cases, like this one, in pretty productive ways. All right, any questions with this first example? All right, rather than stick you on this alone, let's go ahead and go through this together. Since we really have only done this once. Okay, so we're asked to determine the pH of a 0.1 molar sodium carbonate solution. And so again, the key here is we need to determine if there is action toward water. So sodium ion comes from sodium hydroxide, which is a strong base. So because it's a strong base, we can conclude that the sodium ion is inert. So nothing pH oriented is going to come from the sodium. From the carbonate, its conjugate acid is the bicarbonate ion. The bicarbonate ion is a weak acid. And so we can therefore conclude that the carbonate ion itself is going to be basic. So now we set up our base equilibrium. Carbonate ion is reacting with water to make bicarbonate ion and hydroxide. The K value for this is going to be equal to Kw divided by the Ka for bicarbonate, which we're going to have to look up. So we need to look at carbonic acid So carbonic acid, it's H2CO3 would be this one. HCO3 is this one, 4.7 times 10 to the negative 11th. So 1 times 10 to the negative 14th divided by 4.7 times 10 to the negative 11th. To two significant figures, 2.1 times 10 to the negative 4th. So we can see the carbonate ion is a considerably stronger base than what we were seeing with the acidity of the bicarbonate. All right, we need to set up our ice table. What is the initial concentration of the carbonate ion? It is still going to be just 0.1. So again, just to sometimes you have to just remind yourself. So if you break it down like so, if I am starting with 0.1 molar of this, well, stoichiometry is going to tell me that I'm going to get 0.2 molar of sodium, 0.1 molar of carbonate. So it's always something that we just have to kind of keep on our toes on a little bit, especially if there are subscripts. In this case, it doesn't matter, but it's one of those things where it could come into play in other scenarios and in other cases. So our initial concentration is 0.1 molar for carbonate. We're going to lose some concentration of carbonate, gain some concentrations of the bicarbonate and hydroxide. All right, since our Kb value is greater than 10 to the negative fifth, we do want to do a calculation for the 5% rule just to make sure that it is okay to use, because we are going to have a value here. So for 5%, 2.1 times 10 to the negative fourth divided by 0.1 times 100. We're still only getting 0.21%, so we're still very okay to use the 5% rule. But yeah, once we get below that threshold of 10 to the negative fifth, especially with a lower concentration like this, we just want to double check. So we are in good standing to ignore that minus x term. So 2.1 times 10 to the negative fourth is equal to x times x over 0.100. Multiplying by the denominator, 2.1 times 10 to the negative fifth is equal to x squared. Square root, we get x is equal to 4.6 times 10 to the negative third molar. So solving the ice table, we're going to get 0.095 molar for the carbonate ion concentration, 4.6 times 10 to the negative third molar for each of the products. Again, since this is basic, we're going to have to go through the POH route. So the negative log of 4.6 times 10 to the negative third. Two sig figs in the concentration, so 2 decimal places in the POH is 2.34. pH would be 14 minus that. So that'd be 11.66. How are we feeling about this? All right. Let's have you try one here. And then we'll call it a day. So calculate the pH of a 0.015 solution of sodium acetate. Ka for acetic acid is 1.8 times 10 to the negative fifth. That way you don't have to jump to an appendix table. All right, let's see how we're doing. So we've got the equilibrium set up here. The only thing that we are missing is we do not have a value for K. And that value for K would come from dividing 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. So if we do that, we get 5.6 times 10 to the negative 10th. So setting up our ice table, I'm sorry. So setting up our ice table, we've already established that the concentration of the acetate would be 0.015 molar. And with a K value that low, 5% rule is a pretty safe bet here. So we ignore the minus X term here, at least for the purposes of calculating X. We're going to end up with 5.6 times 10 to the negative 10th is equal to X times X over 0.015. If we multiply 0.015 on both sides, we get 8.4 times 10 to the negative 12th is equal to X squared. Square root of that, 2.9 times 10 to the negative 6th molar is X. So solving our ice table, this is going to have no impact on this concentration. So we're going to stay at 0.015 molar for acetate. For the acetic acid, 2.9 times 10 to the negative 6th molar. For hydroxide, 2.9 times 10 to the negative 6th molar. Just like with our other problems, POH is going to be used here. So negative log of 2.9 times 10 to the negative 6th. To two significant figures, POH is equal to 5.54. pH is 14 minus that. So the pH would be 8.46. So in this case, the combination of the fact that the base is considerably weaker, being on the 10 to the negative 10th scale for its KB, and that we're dealing with a lower concentration, the basic tendency is considerably lesser than what we saw in the previous two examples. But it is still greater than 7, so it is on the basic side of the ledger. And we would predict that qualitatively, in addition to doing the calculations here quantitatively. All right. Any last questions here about this kind of calculation? This is a calculation you're going to see a couple of times tonight in the homework, although just as a reminder, homework 14-3 is not due tonight, but rather tomorrow night to give you time to study for the exam, which is first thing tomorrow. All right. The last piece here in chapter 14 just concerns polyprotic acids. We're not going to belabor any of these points too terribly much because, for the most part, your book actually goes into the calculations for how to calculate the pH of polyprotic acids. That's beyond what we're going to do. But what we do want to focus on is that there is one trend in particular that we can look at, and that is the trend that each successive acid reaction for a polyprotic acid is less acidic than the one before it. So if I compare, so for H2A here, if I compare its Ka for the first deprotonation compared to the second deprotonation, Ka1 versus Ka2, what you're going to find is that in every case, Ka1 is better. Ka1 is going to give you more hydrogen than Ka2 is. And in some extreme cases, we're going to find that that is kind of built to the extreme. So if you compare sulfuric acid to hydrogen sulfate ion, big difference there. Strong acid, Ka in the millions and billions versus Ka at like 10 to the negative second. But they're all going to follow that tendency that Ka1 is better than Ka2. And if there is a Ka3, Ka2 is better than Ka3. And so here's a table of values that just kind of that drives that point home. You can see that in some cases, the differences are not terribly extreme. So if I look at citric acid, all three of those deprotonations are within about 100 Ka value of each other. But that's more of an anomaly than anything else. We tend to see that there's usually a pretty considerable drop between the first Ka and the second one in terms of acidity. And this is just a graphic showing how it basically works. So for phosphoric acid, you can see that you have 3 acidic protons because you have 3 hydrogens that are attached to those oxygens, and each one coming off would get its own Ka value. So the first one lost this one, the second one lost this one, the third one lost the bottom one. Technically speaking, because it's 3-dimensional, there's no real true order, 1, 2, or 3, because they're all 109.5 degrees apart. But you see each one is successively being lost. And it always happens in that way. It's a succession. We lose all of the first ones, then we lose all of the second ones, then we lose all of the third ones. Because, especially in these cases, that first one to pop off is a lot easier to remove than the second one is, which is a lot easier to remove than the third one is. So that is it for this chapter. Go ahead and get the last confidence meter point here.